So, good afternoon. So, we already seen the definition of this hyperbolic metric spaces, and we have seen that geodesics in hyperbolic metric spaces diverge exponentially. We have also defined these hyperbolic groups, and so we are left with this thing to prove that this hyperbolicity is quasi-isometry invariant. So to prove that thing, so we need something called stability of quasi-geodesics. Okay, so first let me define. So what do you mean by quasi-geodesics? Yeah. Uh, so a map alpha from a closed interval a b to x. So where this a, it can be minus infinity also, b can be infinity. So these possibilities are also there. And this alpha need not be continuous map. So this is called uh, k epsilon quasi-geodesic. Okay. So if alpha is just k epsilon quasi-isometric embedding. Okay. So meaning of that is, so 1 by k times mod of s minus t minus epsilon is less than equals to distance between alpha s and alpha t, and this is less than equals to k times mod of s minus t plus epsilon. Okay, so this is the definition of my quasi-geodesic. Yeah, so so this will be continuous if epsilon is equal to your 0. Okay, so the simple example, so you can take this map, so alpha x to be your this box of x. So x belongs to your R. Okay, so this alpha, it is a quasi-geodesic in R, or even you can take it in R2 also. So this alpha, so this is a quasi-geodesic in R. Okay, so you can find this k and epsilon here. Okay. So another example. So this already have made. Yeah. So this you can discuss in the tutorial. So you take, for example, you let us take R2, and you take this the straight line. Let us take this x-axis. So nothing special about this x-axis, and you take any point P in R2 and take the orthogonal projection onto this x-axis. Okay, and now yeah, so now you take these 2 points P and Q. So so now you take this concatenation of these 2 paths. So alpha 1 and alpha 2. Okay, so alpha 1, so this is pi of P. So alpha 1 star alpha 2. So this you can prove that. So this is 3-0 quasi-geodesic. Okay, so so what is the this okay, so whenever I say this thing, so this means that, so you are taking the arc length parameterization of this. So this is the arc length parameter. Okay, yeah, so nothing special about this R2. So in fact, in any metric space, so this is true. So if I take x to be, let us take x to be a geodesic metric space. And let us take a geodesic. So let lambda be a geodesic uh, in X from A to B. Okay, and let us take let P belongs to X, and so this pi uh, pi lambda P. So uh, this denote the nearest point. In fact, there can be many. So denote a nearest point projection of P onto your lambda. Okay. So nearest point projection or closest point projection of P onto lambda. So this means that, let me draw this diagram. Yeah. So this is my lambda from A to B. And I have taken this P. And what is this my pi lambda P? So pi lambda P, it is a point on lambda such that, so distance of P to pi lambda P is less than equals to distance of P to X for all X belongs to your lambda. Is it clear? This pi lambda P, it is a nearest point projection. So this is the definition of this nearest point projection. Okay, so in R2 it is just the orthogonal projection. Okay, all right. So now, so again, what I'll do, so I'll take the path, uh, take the yeah. So this geodesic joining P to your pi lambda P and alpha 2. So this is the subsegment of this lambda. Okay, and again you take alpha 1 star alpha 2. Take the arc length parameterization. So this in fact is a 3-0 quasi-geodesic. Okay, so this is an exercise. This we can discuss in the tutorial. Okay, so this is not a geodesic. So this is indeed, it is a 3-0 quasi-geodesic. So K is equal to 3. So in this definition, K is equal to 3 and epsilon is 0. Okay, all right. Okay, so another example. So in upper half plane, so this is my upper half plane with this hyperbolic metric. So take this imaginary axis and take any line like this, which is making an angle theta with this imaginary axis. Okay. So yesterday we have shown that, so this line L lie in a bounded neighborhood of this imaginary axis I, and the vice versa also. Okay. So one can again prove that, so this L is a bi-infinite quasi-geodesic. Fine. Okay. All right. So now let us, yeah. So this we have shown. So L, so there exists K uh, such that, so L lie in this K neighborhood of this I. Okay, and the converse is also true. So this I also lie. So you can find another k prime. Let me take it to k. So this I also lie in k neighborhood of this L. Okay. So this property, is called stability of quasi-geodesics. Okay. So this is true in this upper half plane with this hyperbolic metric. Okay. And if I take any delta hyperbolic metric space, so there also this thing is true. Okay. Yeah. So the proof will follow from this exponential divergence of geodesics. Okay. So let me come to that thing. Okay. So here I have defined. So in this note, so I have defined. Uh, so this lambda epsilon quasi geodesics. So that example I have given it here. Okay. Yeah. So this proposition. So this already I have shared in this that Google document. So what it is saying is the following. So if you take any lambda epsilon quasi geodesic, so it may not be continuous. So this alpha, it may not be continuous, but what you can do, so in a bounded neighborhood of this alpha, you can find a quasi geodesic which is continuous, and alpha and beta share the endpoints. So endpoints of alpha and beta are the same. Okay, so this proof is quite straightforward. So you can look into this proof. So let me repeat it once again. So maybe I can draw it here. So suppose okay, maybe I can do it here. So the proposition is, so suppose you take any k epsilon quasi geodesic, and this is true for any uh, geodesic metric space. So you take any quasi geodesic like this. So this may not be continuous. So image of alpha may be something like this. Yeah. So this may be the image of this alpha. Okay. So what this proposition is saying, so there exists k prime epsilon. So this pair. So there exists this k prime epsilon quasi geodesic, and let us call it to be beta. Okay, so what is this beta it is doing? So it is a continuous uh, k prime k prime epsilon prime quasi geodesic. So it will be something like this. It will be in the bounded neighborhood of this geodesic, this quasi geodesic. Okay, and this beta, so this is k prime epsilon quasi geodesic. Okay, so the proof is not that hard. So this part I have written. Okay, so therefore, so if I given a lambda epsilon quasi geodesic, okay, so without loss of generality, I can assume that quasi geodesic to be continuous. Okay, or so now let us move to the statement of the stability of this quasi geodesic. Okay, so it says the following. So for all delta greater than equals to 0, lambda greater than equals to 1, epsilon greater than equals to 0. So there exists a number r depending on this delta, lambda, and epsilon such that the following holds. So if X is a delta hyperbolic metric space and alpha is a lambda epsilon quasi geodesic in X and beta be a geodesic, with endpoints alpha A and alpha B. So then, so alpha lie in R neighborhood of beta and beta lie in uh, R neighborhood of this alpha. Okay, so though both of them lie in R neighborhood of each other. Okay, so let me again draw a picture. So suppose this is my quasi-geodesic alpha. So this is lambda epsilon quasi-geodesic, and this is my geodesic. Okay, so so they will lie in a bounded uh, neighborhood of each other. Okay, so you have a uniform bound, this R. So R will depend on this delta. So delta is this hyperbolicity constant of this metric space, lambda and epsilon. Okay, so they will lie close to each other. Okay, okay. So how to do this proof? So proof also it is not very hard. So again, by this previous proposition, we can assume this alpha to be continuous lambda epsilon quasi-geodesic. Okay, so we can assume this lambda to be alpha to be continuous. Okay, all right. And let us take this P to be equal to alpha A and Q to be equal to alpha B. Okay, all right. So now what I'll do, yeah. So let me again draw this picture. Yeah, so suppose this is my, so this is my alpha. Okay, so this is quasi-geodesic. And this is my beta. So this is geodesic. Okay, and these are the endpoints. So alpha and beta are from P to Q. So now I'll take this D to be supremum of the distance of x to your, so this is your alpha A and this is your alpha B. So distance of x to, let me write image of this alpha. So x is varying on this image of this beta. Okay. So so what can you say about this thing? So does the, now the question is, so does there exist x naught belongs to your this image of this beta on this geodesic beta such that so D is equal to this thing. So what do you think? Is it true? So in other words, can I get a point here x naught such that so if I take a ball of radius d, so it will be, the picture will be something like this. So it will just the circumference will just touch the alpha and d is the maximum. So is the supremum realized? What do you think? So can I get this x naught? So I have two continuous paths, right? So beta and alpha are continuous. So these are my two continuous paths. And so this is compact, right? Okay, so you have to use this compactness argument to show that, so this x naught indeed exists. Okay, so this is true. Okay, so that thing I have written it here. Okay, so this PQ, it is means that it is the geodesic beta. Okay, so beta is equal to this geodesic PQ, and D is, as I said, so D is the supremum of distance of x to your image of this alpha, and x is varying in this beta, or geodesic joining this P and Q. So there exists x naught such that this supremum D is attained. All right. Okay. So now what you do, so you take an open ball around x naught of radius D. Okay. So you take this open ball around x naught. Okay. So you have this picture here. So you have this picture here. Yeah. Okay. All right. So this distance is your D. So this distance is your D. So this is your, again, it is your D. All right. So now what we are going to do, so I am going to, so suppose I take some point Y, so this Y on this geodesic PQ, and it is lying outside this, so lying outside this ball, right? Because D is the supremum, so there will exist some Y prime such that distance of Y to Y prime is less than equals to D. So this Y prime, it belongs to your this quasi-geodesic alpha, right? Okay, so that thing I have written it here. Okay, yeah. Okay, so first, so this is for any point. So I'll choose this Y to be a particular point. Okay, so what I am going to do, yeah. So I have taken this Y on this geodesic P to x naught such that distance of Y to x naught is equal to your D. Yeah, so what I have done here, so this is my geodesic, and suppose this is my this ball of radius D. So I've taken some point Y here such that, so distance of this to x naught, so this is your twice of D. So if, okay, so if you do not get this point, okay, so if you do not get this point, so that what does it mean? So distance between x naught and P is less than twice of D. So that part I have written it here. So distance between x naught and P, if it is less than D, so then I'll assume this Y to be equal to your P. Okay, and the same thing you do for the other part. So this part also. Okay, so you do the same thing here. So distance of x naught to your Y prime. So this is my twice of D. Okay, and now what we have, so we have this, so this is my quasi-geodesic path alpha. So there will exist some Y prime such that, just 1 minute, there will exist, okay, so this I have denoted by Z prime. Yeah, so there will exist a point Z prime on this alpha such that this distance is your at most D. Same thing here. So there exists Z double prime such that this is at most your D, because D is the supremum. Okay. Yeah. Okay. All right. So now, yeah. So now what you do, so how to apply this divergence, exponential divergence of this geodesic. So exactly that thing I'll not apply here. So I have proved something while proving the exponential divergence of geodesy. Yeah. So let me again go back to this thing. So what we have proved that. So what we have proved that. Uh, just 1 minute. Yeah. So what we have proved that from this exponential divergence of this geodesic. So distance of x naught to your this image of alpha. So this is less than equals to delta times log of uh, length of gamma plus 1. Okay, so let me say what is your gamma. Yeah. So what is your gamma? So gamma is just 1 minute. Maybe I messed up with the notation. Yeah, so sorry. So in the previous thing, so there is some mistake with the notation. Maybe I can change it here. Yeah, so this point I have denoted by z. So this is my z prime and this is my y prime. Okay. So now what I'm doing, so I'm taking this path. I'm taking this path gamma. Just 1 minute. Yeah. So taking this path gamma to be take the geodesic y to y prime, then restrict alpha to y prime z prime, and this again take the geodesic y prime and z prime. Okay. So in the picture, what is the gamma? So the gamma is so y to y prime, and then follow this thing. So this is the subsegment of this alpha from y prime to z prime, and then again come back uh, z prime to z by this geodesic. Okay, so this is my gamma. Okay. So what we have proved while doing this exponential divergence of geodesic, so distance of, so okay, so we have this two geodesic rays. So you can think of this as two geodesic rays. All right. So yeah, so distance of x naught to your this alpha AB is less than equals to delta times log 2 length gamma plus 1. Okay, and okay, so this thing we have shown while doing this exponential divergence of this geodesic. And what is my length of this gamma? So length of this gamma is equal to your, so length of this gamma is equal to your d plus d twice d plus length of alpha restricted to this y prime and z prime, right? Yeah, this is this thing. Okay, and now you are applying that alpha. So this is a quasi-geodesic. Okay, so alpha, it is a quasi-geodesic. So this again you take the parameterization of alpha to be arc length. So then so length of this thing, so this will be exactly sorry, less than equals to lambda times distance between y prime and z prime plus epsilon. Okay, so this will be this thing. So length of this thing will be uh, length of alpha restricted to y prime z prime would be less than equals to lambda times this plus epsilon. Okay, now what is this distance between y prime and z prime? So distance between this y prime and z prime. So this is what, now you come to, yeah, so from here, so by triangle inequality, so distance between y prime and z prime, so this is at most your 60. Okay, so therefore, so what we have, so this length of this alpha restricted to y prime z prime is at most lambda times 60 plus epsilon. Okay, yeah, So we have this thing here. So this shows what? So distance between x naught to this image of alpha. So this is at most this, okay, and also because distance between x naught and image of alpha, it is exactly equal to d, because d is this thing. So d is this. Because of this, sorry. So d is exactly equal to d of x naught to image of this alpha. Okay. So d minus 1 is less than d. So that thing I am using here. So therefore, what we have, so this distance is greater than d minus 1. Okay. So therefore, d minus 1 is less than delta times log 2 of this plus 1. Okay. Okay. So, so from here, so 2 to the power d minus 2 by delta is less than 6 lambda times d plus 2d plus epsilon. So again, observe that. So this in this inequality, the left hand side is exponential, and the right hand side is your linear. Okay, linear in d. Okay, so this will imply that this d, so this will be bounded. Okay, so d as an upper bound, say d naught. Okay, so what we have shown that this d, this d it has an upper bound. Okay, so this d it has an upper bound. All right, so therefore, so this geodesic PQ, so this will lie in d naught neighborhood of this alpha. Okay, yeah, so we have shown this one part. So this geodesic lie in this d naught neighborhood of this alpha. That part we have shown, and the other part is you have to use the connected argument. Yeah, so we have shown that this geodesic is lying in the geodesic PQ. So this is my beta lies in d naught neighborhood of alpha. So now we have to show that alpha lies in some d1 neighborhood of this beta. Okay. Okay. So yeah. So suppose some maximal portion of this alpha. So this I have denoted by this thing. Suppose some maximal portion of this alpha lie outside d naught neighborhood of this geodesic PQ. Okay. So by a connectedness argument, you can prove that so there exists a point W in the geodesic joining PQ, T in this interval A to A prime, and T prime belongs to your this interval B prime to B, such that distance of W to alpha T is at most D naught, and distance of W to alpha T prime is at most D naught. Okay, so from here, so what you will get, that distance between alpha T and alpha T prime is at most to D naught. Again, you apply that this alpha it is a quasi-geodesic. Okay, so from this, what we will get, so we'll get a bound on this T and T prime. Okay, yeah, and from here, so we'll get a bound on this distance between this A prime and B prime. Okay, so we'll get a bound on this thing. So this will prove that length of alpha restricted to this A prime B prime is bounded. Okay, so yeah, so this is the now what you do. So you take the so D1 is this thing. So you take the R to be the maximum of D naught and D. Okay, so this is the stability of quasi-geodesic. Okay, yeah. So now now let us assume that you know the stability of quasi-geodesic. Okay, and from this, so I'm going to show that so this hyperbolicity is quasi-isometry invariant. Okay, so hyperbolicity is quasi-isometric invariant. Okay, so let us take, so let x dx be a delta hyperbolic metric space, and phi uh, be a k epsilon quasi-isometric. Okay, so then the claim is, so then there exists delta 1. So this delta 1 is depending on, so this delta 1 is depending on what? So then there exists a number delta 1 depending on this delta k and epsilon, such that y is delta 1 hyperbolic metric space. Okay, so how do you do it? So we have a quasi-isometry, quasi-isometry x phi from this x to y. Okay, so what you have to do here, so this y, it is a geodesic metric space. So now what you do, so you take any triangle here. Okay, so you take any triangle here. So this is my triangle in y. So you have to prove that this triangle is slim triangle or thin triangle, whatever you. So how to prove this thing? Any idea? So how to prove that this triangle is slim? So using the stability of quasi-geodesic, you have to prove this thing. So phi is a quasi-isometry. That means what? So there exists a, so you know that there exists a quasi-isometry inverse of this phi, right? So this you know, right? So there exists a k1 epsilon 1 quasi-isometry psi from this y to x, such that distance of psi compose phi of x. So this is so less than equals to some, let us take again it to be k1, and for all x belongs to your, so for all x belongs to your capital X, and here for all y belongs to your capital Y. Okay, so this psi is called to be the quasi-isometry inverse of this phi, right? So what is the natural thing now to do? So now what you know, so you have a quasi-isometry from x to y phi, and also you have a quasi-isometry from y to x, right? And let us take this triangle to be my PQR. Okay, so what is the natural thing to do? So you take the image of this triangle under the map psi. So we'll get something. So we'll get something here, something like this. Okay, so this is my psi p, this is my psi q, and this is my psi r. Okay, So what you will get here, so this, you will get a quasi-geodesic triangle here. Okay, so this is PQ is a geodesic in Y, and psi is a quasi-isometry. So image of a geodesic under quasi-isometry, it will be a quasi-geodesic. So you'll get a quasi-geodesic triangle here. And then what you have to do, so now you got these 3 points, right? Psi P, psi Q, and psi R. So you join them by geodesics. Okay, so you join them by geodesics, and you know that X is delta hyperbolic metric space, right? So this blue triangle, so this will be this will be delta slim. Okay, so this will be delta slim, and moreover, so this triangle is your delta slim. Okay, and this quasi-geodesic and this geodesic, blue geodesic. So this red quasi-geodesic and blue geodesic, they are joining same pair of points, so they will lie in a bounded neighborhood of each other. So this is coming from the stability of quasi-geodesic. Okay, so quasi-geodesic triangle is your now delta plus R slim. Okay, and yeah, so psi is a quasi-isometry from that, so we'll get that. So this triangle, so this will be some delta 1 slim. Okay, so this proves that this hyperbolicity is quasi-isometric invariant. Any doubt? Okay, so this proves that the hyperbolicity is quasi-isometry invariant. So now this definition of this hyperbolic group, so this is well defined. So let me come to that thing. Okay, yeah. So again, what is the definition of this hyperbolic group? So a finitely generated group is said to be hyperbolic group or what hyperbolic group if the Kelly graph of G with respect to some finite generating set is delta hyperbolic metric space for some delta greater than equals to 0. And why this is well defined, if I take some other generating finite generating set, then the Kelly graph of G with respect to S is quasi-isometric to Kelly graph of G with respect to S prime. Okay, so and hyperbolicity is quasi-isometric invariant. So therefore, this definition of this hyperbolic group is well defined. So this part already we have discussed. Okay, so now let us move to something else. So properties of this hyperbolic group. So now what we are going to show that, so this hyperbolic groups are finitely presented group. Okay, so hyperbolic groups are finitely presented group. So let me recall what you mean by finitely presented. Okay, so you know that if you take any group, so it is a quotient of a free group, right? So a group G is said to be finitely presented. So if there exists a finite generating set S and a finite relation R such that, so this G is this quotient. So this quotient of this free group, and it is quotiented out by the normal subgroup generated by this R. Okay. Yeah. Okay. So what we are going to show that, so a hyperbolic group G is finitely presented. Okay, and note that by the definition of this hyperbolic groups, this G is finitely generated. So that part we have assumed, and let us take S to be a finite generating set of this G. Okay. Yeah. So yeah. So we have to find this finite relation set R such that given any R in the normal subgroup generated by this R thing. So R can be expressed at finite product of this like this. Okay. So we have to find this. So we have to find this R1, R2, Rn such that R can be expressed as product of this conjugates. Okay, all right. So yeah, so what we are going to show is the following. Okay, so first of all, this part is just group theoretic. So an element G is in the normal closure if and only if that element is identity element in G. Okay, so what we are going to do? So let us take W belongs to G such that W represents the identity element G. Okay, so W represents the identity element in G. Okay, so we'll find a finite set R such that W can be expressed as a product of this conjugates. All right. Okay. So we have taken this W in G. So W will equal to your A1, A2, AM, where this AI, it can be a generator or inverse of a generator. Okay. All right. So correspondingly, I mean, if I in the Kelly graph, so this will give you a loop. Okay, so this W will represent a loop in the Kelly graph. Okay, so this part I have drawn here. So this is my loop. So let us take V naught to be your 1, and yeah. So 1 2. So this V1 is equal to your A1. So A1 is a generator. So yeah, so there will be an edge, and again, so you continue. So this V2, so this will be your A1, A2. So between this A1 and A1, A2, so the edge will be leveled by this A2. Okay, so like this you continue, and yeah. So the last edge, so this will be your leveled by this AM. Any doubt? So I have taken this W to be equal to A1, A2, AM, and it will represent the identity element. All right. Okay. Okay. All right. So now what we are going to do here, so we have this loop. So you have this loop, and you take this vertex. So you'll get this vertex Vi. So Vi is nothing but your A1, A2 up to AI, right? So this is my Vi is this vertex. So what you do, so you join this identity element to this Vi by a geodesic. So this is my geodesic. Okay, so this is my geodesic. And so this you do for all the i's. So yeah, so this you do for all the i's. So we have this two thing here, this geodesic for I plus 1, and this is a geodesic for I. Okay, all right. So again, so now choose this geodesic. So choose the geodesic joining this V0 to V0 to Vi. Okay, so this geodesic. Let us take this geodesic. Okay. And let us call this geodesic to be your Ci. Okay, so this geodesic, I have taken it to be Ci. And again, so this connect this V0 to Vi by geodesic Ci. And on this thing, so you'll get the vertices, right? This is geodesic. So these are my vertices. So the first vertex, I'll call it to be Ci1. The second one is your Ci2, like this. Okay. So these are my vertices. And the same thing you would do it for this Vi plus 1. Okay, all right. Okay. So the end thing, so the end thing, so end vertex, this Vi, so this will be, let us call it to be Ci T CITI. Let us call this thing. Okay. And similarly, we have this thing here. The end thing is this. All right. So first note that, so this length between pi and pi plus 1, because this is an edge, so this is an edge in the calligraph. So length of this thing will be at most 1, right? So length of this is at most 1. Okay. Yeah. So now, sure. Okay. So now what we have, uh, let me, so this is my V0, and this point let us call CITI, and this is my CI plus 1, TI plus 1. Okay. So, and this distance is less than equals to 1. Okay. So let us assume that, okay, so let us assume that this, so Ti I can take in this way such that this distance is exactly equal to Ti, and this distance is Ti plus 1. Okay. So because this is less than equals to 1, so from here, so can I conclude that mod of Ti minus mod of Ti plus 1, so this is less than equals to 1? Can I say this thing?
Yes, by triangle inequality.
Yes, just by the triangle inequality, right? So suppose Ti is less than Ti plus 1, right? So I'll get a point here such that this distance is your Ti, okay? Uh, just one, not 1, I guess it will be 2, right? Just wait a minute. Where it is gone? Okay. Yeah, sorry. So this distance is less than equals to 1. Yeah. So here we, okay. So I'm wrong here. So this distance, so we'll get a point here. So suppose Ti is less than Ti plus 1. So, so what we have done yesterday from that thing. So this distance, so this distance, it will be less than equals to 1. So therefore this distance, so this will be at most 2. Okay. So we have 2 here. Okay. By triangle inequality. Is it fine? Is it okay? So this distance from here to here is Ti, and suppose Ti is less than Ti plus 1. So this distance, so this point, let us take it to be distance Ti from V naught. So by triangle inequality, again, you can show that this dark red portion, so this is distance, length is at most 1. So therefore,
So,
distance between uh, this point and this 2 points, so this is at most 2.
so we should write d of CITI, comma CI plus 1 TI.
Correct.
Lesser
Correct.
equal. The previous one was correct. I mean, this Ti minus Ti plus 1 modulus is less than 1. That was correct.
Oh, that was correct. Sorry. Sorry. Yes. That, okay. Yeah. Thank you for correcting. Yeah. So this part is correct. Yeah. So this is less than equals to 1. So yeah. So this is less than equals to 1. So therefore, distance between CI and distance between this CI plus 1 Ti. So this is at most you 2. Thank you. Okay. Yeah. So that part I have written it here. So let us assume that this Ti is less than Ti plus 1. So let us assume this thing. Okay. So now what we are doing, so again, so we are joining this Cij and Ci plus 1j, again this by a geodesic. Okay. So this we are doing. Okay. So again, let us observe this fact. So now we move to delta hyperbolic metric space. So we have this 2 geodesics, Ci and Ci plus 1. So this is in general it is true. And this is, let us call it to be Cit and Ci plus 1t. So this length is t and this length is your t. Okay, and this distance is your atmos delta. Okay, so this distance is your atmos delta. Okay, now what I do, so if I take 2 points on Ci and Ci plus 1, so these 2 points I will take such that the distance from these points to V0 are same. Okay, so what will be this distance? Sorry, I have made what? So this distance I have taken it to be less than equals to 2, and you know that this triangle is delta slim. So this triangle is your delta slim. Okay, so now if I take some point here, let us call it to be Cit small t and Ci plus 1 small t. So this distance will be at most what? So endpoints, this endpoints are at most 2 distance from each other. So this distance by slimness will be what?
2 delta plus 4. I mean that earlier argument, same argument by.
Yes. So it will be again. So this will be, I guess, what he is saying, 2 delta plus 4. You are saying, right? Okay. So let us take 2 delta plus 4. Okay, by the argument we had given the last class. Okay. So only here. Okay. So therefore, so just make this correction here. So you said that distance between Cij and Ci plus 1j. So this distance is at most 2 delta plus 4. Let us take it to be 4. Okay, so no harm in that. Okay, so each of this length of this thing is bounded and it is at most 2 delta plus 4. Okay, yeah. So what we are going to do, so we are going to split this this whole loop, this W, into the smaller loops, all this thing. Okay, so like you have done similar thing in this Van Kampen theorem. Okay, all right. Yeah, so that thing I have written it here. So now consider the word Ci ai plus 1 C inverse I plus 1. Yeah. Just 1 minute. Ci is what? Yes. So first, let us take. So Ci is the geodesic joining 1 to Bi. Okay. So Ci is this geodesic, right? All this thing. Okay. So what we will have? So you'll get Ci ai plus 1. So it will move like this and come back by this Ci plus 1. So then you will have this thing. I hope this part is, yes, this part I have written it here. Okay, so consider this word. Okay, so this means, so you are considering this triangle first. Okay, yeah. Okay, and yeah, so also note that, so this W, so the W represents identity, right? So this W can be written as product of this, all this. So what of the form like this, the first word will be A1 C1 inverse naturally. So this C1 will be equal to your A1, or you can take just something like this. So so the first one will be your first word is A1 C1 inverse. The second one will be C1 A2 C2 inverse, right? So this W can be written like this. First, observe this thing. Okay. All right. Okay. So now so we are going to look into this subword of this W. Okay, so that is this thing. Okay, so again we are looking into this triangle. So we are looking into this triangle. Okay, so again we are going to split this triangle into your this smaller loops. Okay. Yeah, so this part I have written here. So what we are going to do, so we are going to show that each CIAI plus 1 CI inverse can be written as product of this conjugates. All right. So now, uh, so as I said, yeah. So this part already we have shown. So distance of CIJ to CI plus 1J. So this is at most 2 delta plus 4. Okay. So this is at most 2 delta plus 4. This part we have already shown. Okay. So now you can split. Okay. So join the Cij and Ci plus 1J by a geodesic Aij. Okay. So yeah. So you can name this thing. So this is my Aij. Okay. So now, yeah. So again, what is my Xij? It is Cij inverse Cij plus 1. Just 1 minute. Yes. So Xij is coming from, so Xij is leveled by this. So this edge will be leveled by Xij. Okay. So the edge between Cij and Cij plus 1, it will be leveled by this Xij. Okay. So now what you do, so you take the slope. So you take the slope. Yeah. So this Rij, it is Xij, Aij plus 1, Xi plus 1 inverse J, then Ai inverse J. Okay. So you take this Rij. So this is my Rij. So this loop, so this loop, so this is my Rij. Okay. So this loop is my Rij starting from here. Okay. So what will be length of this Rij? So what will be the length of this Rij? So this will be at most what? So length of
2
this
delta plus
Rij,
4 delta
yes,
plus
yes. First 1 plus 2 delta plus 4 plus 1 plus 2 delta plus 4, right? So it is uniformly bounded, right? Length of this
yes,
Rij.
yes.
Okay. So each of this thing, length of this, all this loops. So this will be at most your this 4 delta plus what 8 10, right?
10. So I have finitely many choices for
Yeah.
Ri.
So now you have, yes. So this is a finitely generated group. So there are finitely many choices of this Rij. Okay. So there are finitely many choices of this Rij. So that part I have written it here. Yeah. So instead of 6, so here it will be 10. So length of each Rij, and in the initial part, so instead of J, you will get some Ri. So that will be also a bounded length. So it will be at most 4 delta plus 10. Okay. So now, yeah. So Rij is this thing. And yes. So again, yeah. We have this picture. Okay, better picture here. So this CI inverse, again, you can write as a product of this thing. Okay, so what is Uij? So Uij is the geodesic word, or Uij. So you take the geodesic joining 1 to Cij. Okay, so Uij is the geodesic word representing this geodesic. Okay. So now what you do, so from 1 you travel to Cij by Uij, now then travel this Rij and then again come back by this geodesic, so Uij inverse. Okay, so you'll get this relation, right? And you can check that. So Ci Ai plus 1, Ci plus 1 inverse. So this is the product of this thing. Okay, so and all this Rij, so these are finitely many choices. So therefore, so what we have proved that. So okay, so again, this W is finite product of this Ci Ai plus Ci plus 1 inverse. So because of that thing, so this W can be written as written like this. So W is finite product of conjugates of R. Okay, so this proved that this group G is finitely present group. Okay, so any question?
Sir, can you explain this? How are we writing this? How are we traveling this this conjugate product of conjugates of Rij? How are you writing this? Can you repeat this one, this last thing? Uij, using Uij.
Oh, okay.
How
So
are
this is little tedious work. Uh, so maybe you can try with
if you
two
can draw
things.
some pictures, that would, yeah, you draw the
Okay, all right. Maybe I'll draw it here. So let us take three of this thing, right?
yes, yes.
Okay.
Okay.
So I'll not. Okay. So first is U1.
Hmm.
So U1. Then so U1 followed by this thing, and then again come back. So what you'll get here, let us call this to be my A1, and this is my what? Just 1 minute. Yeah, the first one will be your just- first one. I think you have to take the trivial thing, right? Okay, so the first one is what starts from here. This one, right? So this is my no. So what I'm doing here is the first one, and the second one is so go here. So there will be some cancellation. That part I'm
Yes,
saying.
yes.
That will be your cancel. So there will be some cancellation. So eventually you will get this thing. Okay. So first, okay. Okay. So let me write down. So let us call it to be some uh, C1. Let us write down this thing, and this we call it to be U1, U2. Let us write like this. This is my A2, and yeah.
The
So
C1, C2 then below.
correct. So this so first one will be E1, A1, C1, and from again, I think I'm a little bit lost
So
here.
these loops we are naming as
Okay.
Rijs, right? The loops are
Yeah.
Rij.
So only this interior thing. So this
Yes,
is my
yes. The whole
Rij.
thing. Yes.
This is my Rij. This is my Rij. Okay, just 1 minute. So actually, so if I just ignore the first well, this first thing, this will be your
We
okay.
should
So
cancel
the
the
first
latter
one,
parts.
okay, just Ri. Just let me check. So Ri1, and the second thing it will be your this. First, if I take this U1 to be your identity, okay, so that you are getting that thing loop, and from just 1 minute. So what I want here, this I want, right? RI1, sorry, RI1, UI1 inverse. Sorry, this will be your 2. Yeah, okay. So I'll come back to this thing later. It should not take. So UIH is this thing. So there will be some cancellation is going on that you
Okay,
have to
sir.
check.
No, you have to
Okay.
start from
Uh-huh.
that point and you have to come back again through the whole thing. I mean,
Correct,
first you
correct,
start
right.
from E naught, you go via U1, then AI, and then come back C1. Then again you
Yeah,
go
sorry, right.
C1 reverse, and then you circle around these, and then you come back to the V naught again, and then you again go. And at each time you want this round in between, right? And then
Yeah, right, right. So
so
U1
at each time you have to come back from you have to come back.
A1 and then U1 inverse I have to take, then
No, no,
U1.
no, no.
Yes, now it is, I think, fine. So now again, if I treble, so something like this will happen. Okay. So again, this U1, U2, something like this. Yeah. So then there's A2, this is my C2, A1 inverse. Again, you have to take this U1, U2 whole inverse, something like this will come. Okay, so maybe you can do it explicitly
Okay.
later. Yeah, it will come.
Okay.
Just you have to
Okay,
write down.
sir. Okay, sir.
Yeah. Okay. So this proves that uh, this is a finitely presented group. Okay. Uh, okay. So another important property of this hyperbolic group is that uh, so if I take any infinite hyperbolic group, it contains an element of infinite order. Okay. So it contains an element of infinite order. Okay, so to prove this thing, so you need some machineries to prove this thing. So there is something called cone type. Okay, so what is my cone type? So cone type of an element of a group. So it is the set of all words V belong to the free group of S. So S is the generating set of this G. So let us start with a finitely generated group G with finitely generating set S. Okay. So yeah. So S is the generating set of this G, and you take the free group on S. All right. Okay. So this word B belongs to the cone type of element of G if distance of 1 to GB is equal to distance of 1 to G plus the length of the word B. Okay. Yeah. So let me draw a picture for this. So let me write down first what is the meaning of cone type. So let us take G belongs to G, this group G, and G is generated by S, and S is finite. Okay. So I say that this B belongs to this cone of G. So if distance of 1 to GB is equal to distance of 1 to G plus the length of this B. Okay. So yeah. So first take this G. So join this 1 to G by a geodesic. And so GB, so this will again be an element of this G, right? This group G. Okay. So join this G to GB again by a geodesic. Okay. So this says that this concatenation of these two geodesics, so this again, so this is a geodesic. Okay, so B belongs to cone type of G. So if this concatenation of these two geodesics is again, it is a geodesic. Okay, so it will be something not like this. So so join 1 to G by a geodesic, and so join G to G by a B by a geodesic. So this path will be leveled by this B, and this distance 1 to GB. So this is smaller. So distance of 1 to GB is less than distance of 1 to G. Okay, so this will not happen. Okay, so clearly, so this concatenation, so this is not a geodesic. Okay, so this concatenation, it is not a geodesic. Fine. Okay. Okay, so now let us some examples. So let us take the free group on 2 generators. Let us take the free group on 2 generators. So this will be your 1. Let us take 1A square. So this, I'm drawing the calligraph. Yeah, so your calligraph is something like this. Okay, so now let me first ask you, what are the all elements which belongs to the cone type of this A? So what will be this? So if some element B belongs to the cone of this A, so this means that, okay, so B belongs to again the free group generated by AB, and distance of 1 to this AB. So this will be equal to distance 1 to A plus length of this B. Okay, so can you give an element which belongs to the cone type of this A? And can you give an element which does not belong to the cone type of this A? Yes, please give at least some element which belongs to this set.
A is there.
Okay, so you are saying this A is there, right? Okay.
Yes.
So this means what? If A belongs to this thing, so this means 1 AA. So that is A square, right?
Yes. Yes.
This distance is equal to distance of 1 to A plus length of A, which is equal to 1.
Yes. Right.
Right? So yeah, so that is clear. So
A
first take
inverse is
geodesic.
not there.
Yes, correct. So you take the geodesic joining 1 to A, and then again you follow this geodesic. So this total thing will be a geodesic. Therefore, A is there. You are right. And you are saying that A inverse, it does not belong to the cone of A. So that all of you agree? So if I take, suppose A inverse belongs to cone of A, so then what I am doing, so again I am returning back. So after traveling from 1 to A, again I am coming back to this 1, right? Because A inverse is 1. So that is that path is not geodesic. First you travel 1 to A, and A to A inverse, you again come back, you return to identity, so that is not a geodesic. So A inverse, it does not belongs to the cone type of this A. Okay. So you have shown that A belongs to cone of A. Any other element?
Any element which lies on this left side would not be in the cone, I think.
Left side means this one.
No, I mean left side of 1.
Okay.
I mean this A inverse squared.
Okay. Okay. Yeah.
I
So
mean any word starting with A inverse at least. Those things.
so any word which starts with A inverse, it will not be in the cone that you are saying, right?
Yes, yes.
Yeah, that part I agree. Okay. And what will lie? What is this full set? Can you describe it? So now if I take, let us take, so this is, so this what is what? This what is your AB, right? This vertex is
Yes.
AB. Okay, so now let me ask you this question, whether this AB, it belongs to, or B belongs to, let us, does B belongs to cone of A?
Yes.
Sorry?
Yes, it belongs to them.
Yeah, so this will belongs to the cone of A. So what you do again, so travel from 1 to A and travel A to AB. So this is geodesic. This is geodesic, right? So AB, it belongs to cone of A. Similarly, if I take AB inverse, B inverse also belongs to cone of A by the same reason. And if I take any point, so let us take some A to the power N. Yeah, so N is greater than, so 1 obviously it belongs to cone of A. And if I take any A to the power N and take any word here, W, so that W will belong to the cone of A, right?
Yes, yes.
So this W, it will belong to the this cone of A. So you can take this geodesic. So this is a unique geodesic space. So this W, it belongs to this cone of A. Okay. So therefore, yeah, so we have a description of this set, right?
Yes.
Yeah. So the starting word, it should not be your A inverse. Okay. So starting word of W, if it is not in A inverse, it belongs to the cone of A. Right? Okay.
Yes, yes. So it will be write down the set expression. No. In terms of
We can write down the expression that what I have written here. You can see. Yeah. So all this thing, it belongs
okay,
to
yes,
this.
yes. Exactly.
Uh-huh. Okay. Okay. All right. Good. So yeah. So now let us move to. So this you now know, right? What is this thing? So what is cone of B? What is cone of B? What?
Similar thing. Yes.
Okay. Similar thing. What will be cone of 1? It will be the. What is cone of 1?
whole feet,
Say it again.
because one is anyway
One of one will be everything.
Yeah. So cone of
sorry,
1
sorry.
will be all reduced words, right?
Except
All,
one.
1 will be also there, right? All reduced words. You have to take reduced words.
So identity won't be there in the cone of one, right? I mean, one won't be there
Why?
because distance between one and one is 0, and I want distance between one and one is equal to distance between one and one plus
So
one.
length of 1, I will take it to be 0.
Oh, okay.
Length of identity element is 0.
Okay.
Okay. So all reduced words you will get. Okay. So similarly, you will get. Okay. Now let me ask you this question. What will be cone of A square? So what will be cone of A square? So let me draw a fresh
It should
picture.
not be.
Uh,
It should not start from a to the power minus m, where m is positive. Remember.
So same as cone of A, I guess.
yeah, so it will be again same as cone of A. That is, so observe this thing. So cone of A square is again exactly same as cone of A, right? Okay, so now if I take this collection of sets, so cone of W, so W is a word in this free group. Okay, so what will be this set? Can it be infinite? If it is finite, how many points will be, how many sets will get here? This is a collection of sets, right? How many things you will get?
The last element, I mean, last element in the reduced representation of W, it will be the cone of W will be dependent on the last alphabet in the.
So you'll get, so this set is nothing but cone of A, cone of B, cone of 1, cone of
A
A
inverse.
inverse, and cone of B inverse. Okay, so we'll get this 5 thing only. Okay, so therefore the collection of cone types, so this is a finite set. Okay, so this is a finite set. So now if I take a hyperbolic group, so this is a result that the number of cone types for hyperbolic groups is same. Okay, so that thing I have written here. So that theorem, I think it has been proved by Cannon, I guess. Yeah. Yeah. So a hyperbolic group has only finitely many cone types. Okay, so this can maybe can do tomorrow. So this has finitely many cone types. So using this thing, so one can prove that hyperbolic group has an infinite order element. Okay, so I'll stop here. So if you have any question, you can ask. Okay, so then again we meet at 4 o'clock, right? Okay, so we'll start tutorial at 4 o'clock. Yeah, please stop recording.